Thank you, Libby. All right, guys. So to begin with, I'm sorry that I cannot zoom in on this more. If you want to have a better look at this little animation, I started a meeting and you can join the meeting. But I don't know, have you ever seen a tuning fork before? It's shaped like this, kind of like a Y, and it's metal, and it is built to vibrate at an exact frequency, which gives it a perfect pitch, unless it's broken. But this allows people to tune their instruments, right? It's used a lot by a piano tuner and things like that. But at any rate, what I like about this animation is it shows how the vibration of the fork itself causes the air molecules around it to vibrate. Can you see the zones of compression and zones of rarefaction? Compression where it's dark because the air molecules are all squeezed together, huh? And rarefaction where it's lighter because the air molecules are spread apart. Are you good with that? Next, I want you to notice when the fork stops vibrating. Just there's a moment right now and right now when it's not vibrating, right? And I want you to look at the air molecules when it's not vibrating. You see they're all evenly spread across the animation? They're evenly spread out, right? So that's the way the air molecules would be without something vibrating next to them. Does that make sense? So this is a nice demonstration of the way sound actually works. Okay, so this is what I want you to visualize sound waves as actually looking like. I've been drawing them as parentheses. Could you see how I could convert those into a bunch of parentheses together? Right? That's a little more accurate. Sometimes I just use our normal wave shape to show what's going on, but this is really what's going on, huh? Does that make sense? Okay, I assume it does. Let's have a look at the project, which is due today, right? Yeah, today's the last day for all of your work. That was posted on Teams a week ago. So we've done most of this together. Some of it I've asked you to do by yourself. Hopefully you did. That's called homework. All these pages with my musical instrument collection were to be done at home, huh? This one was to be done at home where you watch the video of the vibrating powders. Then this one, pages 10, 11, 12, 13, 14, 15, we did this all together. Except for page 15 when it's a summary. Well, wait a minute. If it's a summary, doesn't that mean we've already done everything and you've been introduced to all the ideas? And therefore you should be able to do it by yourself? Which is what I asked you to do. I actually asked you to start on this on Monday and then to finish it on Wednesday. Okay? So that's where we left off. Now, that leads us to the last couple of pages. Notice the subtitle says, these are the final conclusions and review. Once again, there's really nothing new on here, but there are a couple things that are tricky. And so I want to help you with the tricky questions, but I'm not going to go over every single question. Does that make sense? And really the most important thing today is to get ready for our final exam. So what I want to do with you guys is a few questions together on this, and then we're going to spend the rest of the period finishing up on the stuff for the final. Now, you might not have enough time to finish all of this if you haven't done some of it at home. You should turn in whatever you do have done, though, because you don't want to end up with a 0 on it, huh? Right? And you can work on it tonight after school, too. But the door is closing, huh? So, a couple things I want to help you with. Number one, describe how either an animal or a piece of technology uses ultrasound or infrasound. And you might be wondering, wait a minute, when did we talk about ultrasound and infrasound? Well, the truth is, we read about it way back here on page 4. So if you did that homework assignment that I asked you to do, you could actually answer this question right now. But I found a pretty interesting graph that I want to show you that will help you work on this as well. So let's look at this graph. Here it is, showing the different frequencies of sound waves in hertz. Starting at 0 hertz, 0 vibrations, would that be a sound at all? If there's no vibration, there's no sound, right? Just prop that open for me now. Those guys are out of the hall. It's out there. And it goes all the way up. Wait a minute. 2 kilohertz, 20 kilohertz. What's the kilohertz? You see kilo, that means 1,000. So this is really 20,000 hertz. 20 M hertz, megahertz. That's 1,000,000 hertz. 20 G hertz, gigahertz. That's 1,000,000,000. Okay? Can we hear that entire range from 0 to 200 billion?
No.
No, we cannot. What is the range of human hearing? Well, look down here on number 9. Yeah, what is it? Do you remember? Is that what this is showing?
Yeah.
Yeah, 20 is the lowest we can hear. 20,000, 20 K hertz is the highest. And notice this one up here, number 2, that says acoustic. That's what that means. If it's acoustic, it's within the realm of human hearing. Does that make sense? Yeah.
So I was wondering, is a dog whistle infrasound or ultrasound?
Well, let's look at that. Let's look at the diagram. Number 9 is acoustic, human hearing.
Yeah.
What's below that? Infrasound.
Yeah.
What's above that? That's where the dog whistle is. A higher pitch than we can hear. Now, there are some animals that can detect infrasound below our ability to hear it.
Bats.
Well, bats mostly use ultrasound.
Oh, yeah.
But infrasound, my favorite example is the elephants. Is that what you said? Yeah. So elephants can hear a lower pitch than we can. Imagine a subwoofer and you're feeling the vibration, but you're not hearing it, but you can feel it. Have you ever experienced something like that? That's like infrasound. And elephants actually communicate with these long grumbles and grunts using infrasound. We can't hear it, but we can record it, huh? And then we can actually make a visualization of it with a computer. But it's kind of crazy because elephants, with their infrasound, can communicate with each other when they're over a mile away. And the thing that it turns out that part of their ability to hear these really low sounds is they have sensitive feet. And the sound vibration gets picked up by the ground and carried through the ground, and the elephant can feel that vibration in the earth. Which, in a way, is really cool if they're living in the jungle somewhere and far apart, right? But it's also, I think, pretty sad if you think about elephants in a zoo in a big city where there's trucks rumbling down the freeway 24/7. What would that do to an elephant? Wouldn't it drive him nuts? Yeah, I think it would drive him crazy. So elephants can hear infrasound. Bats and dogs and other animals, in fact, doesn't it say right there, animal hearing, can hear ultrasound. But if we even go beyond them, we can start using these extremely high vibrations for a variety of purposes in different technology. So for example, right here, therapeutic ultrasound. This is when they might have a device that puts sound waves into your back to loosen up tight muscles. You wouldn't hear it though, because it's above your range of hearing, huh? Ultrasound. In fact, you know about that. How do we see, what's the first picture taken of most babies anymore? An ultrasound, right? The vibrations are so high we don't hear it, but we can create an image out of the way that those vibrations bounce back. If you've had your teeth cleaned by a dental hygienist, they often use an ultrasonic cleaner. The high vibrations blast the plaque off of your teeth without damaging the teeth themselves. Does that make sense? And of course, they actually have to have it at the right frequency, don't they? My wife is a dental hygienist, and she talks about her tunable ultrasonic cleaner. She can adjust the frequency to match the person's teeth and plaque, right? So it gets rid of the plaque without damaging the teeth at all. Okay, so does that help you with that first question? Describe an animal or a piece of technology, right? Not really going to give you time to work on it because we've got a lot to do today. Number 2, choose any musical instrument. Well, that's when you go back to the video I made of all those musical instruments. What I call it, a world of sound video, right? Yeah. But I do want to help you with number 3. Okay. The main point of number 3 is knowing about octaves. So have you heard of octaves in music? Okay. So for example, if we have a piano keyboard, it has 8 notes. I need to draw one more over here. Let's say we start at C. What happens when you get to G? You go back to A, don't you?
Yeah.
And the 8th note over, notice 1, 2, 3, 4, 5, 6, 7. The 8th note is another C, isn't it? It's 8 notes, so we call it an octave. But do they sound identical? No, one is a high C and one is a low C, correct? Right? Yeah. Here's the deal with an octave. However many vibrations this is, whatever its frequency is, and let's just say that it's 500. I don't know exactly what it is. You take that 500 times 2, and that's the vibration of the next C in the scale. So that would be 1,000. That would be 1,000 hertz. So to change octaves, to go up an octave, you have to multiply by 2. To go down an octave, you have to divide by 2. So what's the next C higher than the one I drew on the board over there? 2,000. And the one after that? 4,000. What about the next C lower than this 500 hertz? 250. What about the C lower than that? 125, right? Okay. Are you with me on how to figure out octaves? You just double. Now look at the question, number 3. We can only hear between 20 hertz and 20,000 hertz, right? So how many octaves can we actually hear? Well, let's start by doing this. 20 is the first octave, right? Can we hear 20? Divide by 2. What do you get? Can you hear that octave? No, so we ignore the 10, huh? We can hear 20. Now, how do we go to the next octave up? Double, which gives us, can we hear that? Yes. So now we've heard 2 octaves, huh? What do you do to get to the next one? Double 40, and you get 80. We can hear that, huh? Double that to 160. We can still hear that, right? So you have to count how many doublings we have between 20 and 20,000. Go ahead and take a minute to do that now. Okay. How many times can you go 20 times 2 times 2 times 2 times 2 times 2 without going past 20,000? 20 and then 40 and 80. Did you count 20? Oh, I don't want any points. It's just how many doublings. How many doublings? 20 counts as the first one. Okay, count the first one. 20, 40, 80, 160. Okay, you take it from there and count how many times you double. Do it yourself. Ready, set, go. Jacob, do it yourself. 20 times 2 times 2 times 2 times 2 times 2 times 2 times 2.
Sometimes concert tuning is.
Times 2 times 2 times 2. How many times can you do that but not cross that 20,000?
No. Go one more. No, you get 20,480.
Oh, no.
That's not on. Huh? That's not on. Yeah, that's not. It's 10,000. Yeah, but then if you multiply one more time, that becomes 11. 20 counts as enough. No, it's 9 times and then the 10th time goes over 10.
But did you count 20
As an
first
octave,
time?
that's
I think you skipped it. When I first did it, I counted 9, and then I know that one that I started with should count as number.
Oh, so yeah.
So it's not how many doublings, it's how many numbers count, so 20 counts.
So yeah, and with that, I got 10.
Yeah. And you should be able to solve question 4 the same way. So here's the deal. I said that this was 500. I know that's actually not true. That just was an easy example to work with. What is true is that when modern concerts tune up, they define A as 440 hertz. They call it A440. Okay? Now, not all tuning was 440. Some other cultures use a different number of frequencies, a different number of vibrations. Even Western music 500 years ago, it was like 432, slightly flat of what we hear now. But today, concert tuning is considered to be A440. So what is the A that's lower than that? 220. What's the A lower than that? Can we hear those? Yeah. What's the A higher than this? 880. What's the A higher than that? Double it. You get 1760, but that's okay. My question for you is, how many hertz for the lowest A that we can hear? And how many hertz for the highest A that we can hear? Are you with me?
Yeah.
Take 440, divide by 2, divide by 2, divide by 2. You can't go below 20 though, right? Go back to 440, double it, double it, double it, double it. But you can't go above 20,000. So don't tell me how many octaves this time. I don't want you to count octaves. I just want to know the lowest frequency A that we can hear. And I want to know the highest frequency A we can hear. Yeah, you haven't done number 3. And number 4 is not what I'm looking for either. Thank you. So Alan, for number 3, are you ready? Are you ready? You got to count. 20 is the first one. Times 2 makes what? That's the second one. Times 2. Times 2. 40 times 2. Multiply by 2 every time. That added 20. I want you to multiply by 2. No. What's 20 times 2, Alan?
40.
Yeah. What's 40 times 2? No, that's 40 plus 20. That's 40 times 2. 4 times 2 is
16.
40 times 2. Just funny. Yes. Okay, so we have 20, we have 40, we have 80. Now I have to times that by, take 80 times 2, what do I get? 160, right? I keep doing this and I have to count how many times I've gone times 2. until I get to 20,000. Once I get there, I have to stop. Or before that, I can't go past that. My answer, if I only wanted it to here, I would say 4 times. Didn't get it? So you have to count how many doublings can you go without crossing 20,000. This one was 4. Okay. So hopefully you found an A that was still an A, right? It still had to be an A, and you gave me the number of hertz. The lowest possible A that we could hear. Also, you gave me the number of hertz in the highest possible A that we could hear. Right? That takes us to number 5. Inverse relationship between wavelength and frequency. Okay, so I'm going to draw some stuff on here, and this is not the answer to these questions, but it's something you should look at to help you figure out the answer. Okay? So I'm going to draw 2 waves, and I just happen to have space right here. Here's my first wave. And here's my second wave. Not very good, but that's about as well as I can do it right now. All right. So tell me this. Which wave has a higher amplitude? Be careful. Amplitude. What does that mean? What does amplitude mean? Yeah, Libby? The volume. Yes, amplitude means volume. And when you say size, do you mean this way? Or do you mean this way? That's right. Amplitude is how tall it is. Now, I was trying to make them about the same. It looks to me like the first one was a little taller than the second one, huh? I didn't draw it very well. They were supposed to be the same volume. Which one is going to be a higher pitch, though? Can you tell which one's going to be a higher pitch? Yeah. Which one? Why?
There's more waves.
There's more waves. Let's count them. How many waves are in the top one? Count how many peaks there are. 1, 2, 3, 4. I counted 4 peaks for the top one. How about the bottom one? 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to ignore that last one.
12 and a half.
Yeah, 12.5. I'm just going to call it 12. Now that is what we call the frequency. The number of waves is the frequency. Does that make sense? We would call it that?
Yeah. The
number of waves is the frequency. But there's another measurement we need to talk about called wavelength. I'm just going to call it WL. Now look at this. If I take a line and I draw from peak to peak, that's the wavelength. From one peak to the next is the wavelength. So look at the wavelength on this one. It's that big. On the other one, I draw a line from peak to peak, like that about. And how long is that wavelength? A lot shorter. But wait a minute. The frequency was a lot higher, wasn't it? So look at the relationship here, you guys. When frequency increases, the wavelength gets smaller. When one goes up, the other goes. And what do we call that relationship? If they're opposites, it is inverse. So when frequency increases, wavelength decreases, right? Or vice versa. When frequency decreases, wavelength increases. And then I'm going to leave you to figure out 6 and 7 for yourself. Describe frequency and wavelength about these different notes. And that takes us to this paragraph at the bottom of page 16. So I'm not giving you time to answer all these questions right now, am I? No, because we got to be ready for our final exam. But I am giving you some hints of things to think about for the different questions, right? So please jump ahead with me, stop what you're doing, and jump down here to number 8. Okay. As well. Okay, during these activities, we discovered that all waves travel at the same speed, even if they're different pitches or amplitudes. That's what we did last class, wasn't it? Didn't we find basically that the speed of the wave stayed the same, regardless if it was a high or a low pitch? And we found that the amplitude did not change the speed of the wave either, did it? If it was loud or quiet, it still traveled at the same speed. So this is true for any single type of wave moving through any specific medium or material. For example, loud and quiet sound waves all travel at the same speed through air. Doesn't matter if it's loud or quiet. If it's going through the air, they travel at the same speed. However, different kinds of waves, like light waves versus sound waves, move at very different speeds. Wave speed also changes when traveling through different materials. For example, sound waves travel much faster through water than through air. Okay? And Mr. Mayer brought up an example of this. Have you ever seen like an old movie where somebody puts their ear on the train track to listen for the train? Think about how that would work. The sound wave gets transferred through the metal of the track much faster than it travels through the air. The vibration gets sent right through the metal. And if you put your ear up against the metal, you'd be able to hear it before you could hear it coming through the air. Does that make sense? So waves travel at different speeds through different materials. We're going to talk more about that in the future. But look at question 8. Imagine if high and low pitches did move at different speeds. What would this do to the sound of music performed in a large concert hall? Think about it. At a big concert, somebody way in the back. What if the bass notes from the bass drum and the treble notes from the guitar did not travel at the same speed? Would the music be synced up correctly? Or would it be fragmented? Okay, so that's what number 8 is asking you about. Just imagine if they didn't travel at the same speed, what would it be like to listen to that music? So there's a couple more here I want to help you with before we start our review for finals. Okay, question 9. Sound travels through air at a velocity of about 750 miles an hour, but light travels so much faster that it reaches our eyes almost instantly. I want you to calculate the distance to a lightning strike if you counted 5 seconds between the flash and the sound of the thunder. The flash is when it actually happened, huh? Almost instantly gets to you. The thunder takes longer to get to you, though, doesn't it? So here's what you have to do. You got to get out a calculator. And what we know is that sound travels about 750 miles an hour. So you're going to put 750 into your calculator. But wait a minute.
Oh, like 7.50?
But wait a minute. What did we measure how long it took to get to our ears from the thunder? Did we measure that in hours? We measured it in seconds, didn't we? So the first step we have to take is convert this 750 into not miles per hour, but miles per second. So you take the 750 divided by the number of minutes in an hour. How many minutes in an hour? Okay, that gives you miles per minute. Are we done? No, because we need miles per second. So you took your 750 divided by 60. Now we have to do what? Divide by another 60 to get miles per second. But wait a minute, and that gives us the number of miles that the sound travels in 1 second. But how many seconds did it take to get to you? 5. So what are you going to do? Multiply by 5. And that's going to be your answer to number 9. It's going to be in miles. That's going to be measured in miles.
So we should like the distance.
Just slightly more than a mile,
Okay.
right? And this is connected to question 10. All you have to do on question 10 is fill in the blank. Develop a simple way to estimate how far away lightning is from you. How can you tell how far away lightning is from you? If it's a 5-second delay between the flash and the crash, how far away was it? What did you just calculate? If it's a 5-second delay, how far was it? That was about a mile, huh? Just so much, slightly more than a mile, but so much little more, you might as well just call it a mile every 5 seconds, huh? So how far would the lightning be if it took 10 seconds for the thunder to get to you? It'd be 2 miles away. What if it took 15 seconds? 3 miles away. What if it took 2 seconds? Less than half a mile. What if it only took half a second? You better take cover, huh? That's not actually possible. It could be virtually instantaneous, but the sound could never reach you before the light. There's lots of what ifs, huh? Yeah. So, but that isn't anything about how far away it is it? Does that make sense? Then we're going to go down, and I want you to notice on 11 and 12, they both have to do with the amount of energy in sound waves. So think of the wave as a disturbance moving through a material, like in that video of the tuning fork I started class with. Did that seem like a disturbance moving through the material? Okay. We can also think of a wave as a way to transfer energy through the material. And I want you to just think for yourself, do you think loud or quiet sounds would have more energy? Do you think high pitch or low pitch would have more energy? That's all you have to do for 11 and 12. 13 and 14 should also be straightforward. They should be review questions. Let's move on to page 18, the last page. So if you look at this last page, do you see there's 4 different sound waves on here? Right? Some of them are tall, some of them are small. Do you also notice that some of them have a lot more lines in them than others? Yeah. So on here, tell me which 2 are the quiet waves? If we just counted number 1, 2, 3, 4 from top to bottom, which 2 are the? Do this for me. Show me with your fingers. One hand has either number 1, 2, 3, or 4. The other hand has the other one. Which are the 2 quiet ones? Okay, you should have number 1 and number 4. Those are the quiet waves, aren't they? How can you tell they're quiet? Because they're not very tall, are they? In other words, their amplitude is Yeah. So up here, all we have to do to answer this is say that it has a short amplitude or a low amplitude. Frequency we'll come back to. What is that short? Well, let's go ahead and do frequency. Look how many waves there are. Can you see that these two match? Aren't these the same? Yeah. What about this one? Does it match the one above it? No. Does it match the one below it? Yeah. So which, the top two or the bottom two, have a higher frequency? The bottom two have the higher frequency, right? There's more waves per second, more hertz. So for this one, number one, we're going to say this frequency is low, at least compared to the other ones in the diagram. What about volume on this one? How loud is number one? It's quiet. We can tell because it's not very tall. And what's its pitch? It has a low bass pitch, right? That's all you have to do for this. But I will point out at the very bottom, there is one more question you might not see. So don't skip that last question at the bottom of the page. I'm going to give you 5 minutes to finish this page, and then we're going to go work on the final exam review, because we got to go over some stuff we did way back in August and September that will be on the final, right? So just finish up this page, 5 minutes. I'm going to turn on some music. When the music stops, we're going to move on to a new topic. Yes. Don't take long though, you don't want to miss the review. Okay, you don't have to draw those. I was just doing that to help you think about it. Okay, so let's look at my drawings again. These are not the answers to these questions. It's to help you understand how to answer them. Okay, so can you see that this only has 4 waves? So its frequency is 4. This one I counted and it has 12. Then I took this line. And what is this line? It was the distance between waves. See that? How it's from peak to peak? You don't have to draw this. I just want you to understand my words. We call this wavelength. See that? WL, wavelength. What about this one? Does that look like the right wavelength for these guys? Yes? Well, somebody's yeah. Look at that. Do you see that that goes from one peak to the next? So this is the wavelength for the bottom line, for the bottom wave. Which one has a short wavelength? The top line or the bottom top wave or the bottom wave? Which one has a short wavelength? Short wavelength. Yeah, can you see that? It's only from here to here, huh? This one's way from there to there. Much bigger wavelength. Right? But which one has a higher frequency? Look at the numbers. Frequency. The bottom one has a big frequency, but it has a small wavelength. Is that true? Small frequency, but big wavelength, huh? Big frequency, small wavelength. When one goes up, the other goes down, and we call that the inverse relationship. So you need to describe that inverse relationship for question 5 in words. question 5, right? If you're lost on question 4, that's a totally separate conversation. Well, song's over. That's all the time we have to work on the project. That was a new song. So I would like you to close the project. Save what you've done, right? Sounds like if you're not done, you might need to do some work at home on that. Tonight is your last night to finish it, huh? But at this point, we got to get going on the review for the final exam. We good? Okay, so let's look at this. Your final will be one giant story problem that combines the 4 major topics that we've had. F equals ma. What's that stand for?
Force equals mass times acceleration.
Good. Force equals mass times acceleration. Number 2, energy. What does that stand for? PE plus KE equals ME? What's PE? Potential energy plus kinetic energy equals, good, mechanical energy. Then we did momentum. P equals MV. What does that stand for? Mass times velocity. Momentum is mass times velocity. And then we studied sound, huh? Okay? So when I say it's one giant story problem, I'm not going to write out the whole problem on page 1 and make you turn back to it every time. Instead, I'm going to keep adding new details to it. Now, if there's 4 topics, each topic is going to be about a page on the final. How many pages will it be? It's 4 pages long, but I have to add, there is also an extra page because we have to make a graph as part of it. So it's going to be 5 pages. All right. So here's our example. This is our example problem, right? Like if you get the final exam, it starts right here. Joe and Kamala went snowboarding. Joe has a mass of 86 kilograms, while Kamala's mass is 61 kilograms. They took turns timing how fast they rode down a slope that was 89 meters long with a vertical drop of 26 meters. Hey, wait a second. I just gave you 2 distance measurements, didn't I? Let's look at this diagram. Which of these is the 89 that they skied down, that they rode down? Yeah, it would be this, huh? 89 meters. That's what they actually, that's the distance they actually went, huh? So what's the 26? What's this 26 in here? There it is. A vertical drop of 26 meters. What is that? If they were like bungee jumping or skydiving, it would be this one, wouldn't it? It would be how far downhill they went. Does that make sense? Call it vertical drop. Like when I go ski, I like to track how much vertical I did that day. Joe took 17 seconds while Kamala took 20 seconds to ride down the hill. Are we good with all that? Okay. Now think about this. Some stuff we measure. Some stuff we calculate. We have to do math. Some stuff we have to make a decision about before we begin the experiment. So what do you think? Velocity. Did we measure, calculate, or make a decision about that at the beginning of the experiment? Velocity. Did we measure their velocity? I would totally agree. We've measured their velocity. Well, excuse me, that's not right. We didn't measure it. We have to calculate it. My mistake. We have to calculate their velocity. We don't know what it is until we do the math, correct? What about mass? Well, we don't decide what Joe's mass is. We have to measure his mass. What about acceleration? We have to calculate that one. We have to do some math. What about the time it takes to get down the slope? Did we start and stop a stopwatch to measure that? Yeah, that was a measurement. What about who goes first? That's what we decided, huh? And then the distance they ride, what was that? Well, we can decide we're going to go from here to here, but eventually you're going to have to measure it, right? Are we good on that? You see why I put CM and D on there? Calculate, measure, or decide. Next, we're going to make a data table. Here's a hint. Any decisions should go in the table first. Okay, let's just do that. What decisions did we make? Yeah, so I'm just going to put the person is our first column. And then I'm going to go ahead and fill in right away Joe and Kamala. Okay? Any other decisions that we made? Or was that it? That was it. Next, we should have measurements. So what measurements do we need to fill in?
Mass.
Yep, we need a column for mass. What's next? We need a column for time. And we need a column for distance. Lastly, we include calculations. What do we need for calculations? We need velocity. What else? Acceleration. And I didn't say it up at the beginning, but there's going to be one more calculation to do, and that is force. So what I want you to take a minute to do on your own right now is I want you to go back to the story problem, and I want you to pick out the numbers in order to fill in the measurements. All those numbers were given to you. All the measurements are there. Don't do the calculations yet, but find the masses, find the times, and find the distances. Go ahead and fill those in right now. Just so you know, this is exactly what your test is going to look like. It's not going to be Joe and Kamala. In fact, they're not even going to be snowboarding. It's going to be a different story problem with different numbers, different situation, but you approach it the same way as this. So make sure you know how to do it. This is a practice test, basically. Fill in time, mass, and distance right now. Ooh, distance. Which distance are we going to use? Which distance are we going to use?
89.
Yeah, we're going to use the 89 for distance. We'll use the 26, the vertical drop, we'll use that later. Yeah, we'll use it for that. We'll also use it for acceleration. Well, you gotta look at the problem. Let's see, what was Joe's mass? Joe has a mass of 86 kilograms. That was an easy one. While Kamala's mass is 61. It's right there. All you have to do is look for it, huh? Time. What was Joe's time? 17 seconds. And Kamala was 20. Let's see, distance. How far did they go? 89? Was it the same for both of them? They both went 89, huh? So there's all the measurements we filled in already, huh? Just have to copy them down. Next, look at question 3. It gives you the formulas, and I will give you these equations. You just have to know how and when to use them. So you get these equations to fill in velocity, acceleration, and force. So go ahead, get out your calculator and start calculating. V equals 2d over t. What's V? Velocity. What's d? Distance. What's t? Time. Anybody need a calculator?
Wait, is that 2 times the distance?
Yep.
And then times?
Nope.
Or divided by time?
There's a slash there. That means divide, right? 2d divided by t. Well, we're reviewing for the final. It doesn't seem like a good decision to leave to me. 2 times d divided by t. 8.9. Yeah, we gotta talk about that. Let's see, for Joe's velocity, did you get 10.47? Which I'm going to round off to 10.5. What about Kamala? 2d divided by her time, divided by t. What do we get? 8.9. And I hope you're staying with me because you need to be able to do this by yourself next class, huh? Well, not next class. We have one more review day. Next, what's A stand for? Equals 1/2 parentheses v squared. What's v? Velocity divided by h. What's h? Height. So wait a minute. I don't see height on here. Where's height? It's this 26, isn't it? Okay. So this is the trickiest one in the chart. You have to start from inside the parentheses and work your way out, huh? First thing you do is put V into your calculator. So let's do Joe together if you need to. 10.5. And then either find your x squared button or multiply it by itself. 10.5 times 10.5 or 10.5 x squared. I get 110.25. Yeah. Okay. That was the v squared part. Now I divide by h. What was h? Oh, I don't show it up there anymore. I better show it. There it is. What's the height? The 26, right? So I'm going to take that 110 divided by 26. I hit the equal sign. I get 4.24, blah, 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 blah. Right? Am I done? No, I have to multiply that by 1/2. I either multiply by 0.5 Or I divide by 2, they give you the same thing. I like divide by 2 myself, and I get 2.12. 2.12. Is that what you guys have?
2.1.
That's interesting. Maybe you rounded something off.
I used 10.47 instead of 10.5.
Okay, that's why. Yours is actually more accurate then.
Ooh.
Yeah, if you use 10.47, it would be more accurate than my 10.5.
What's acceleration again? Is that? What do we use? Do we use meters per second?
It's meters per second squared. Where'd the half come from? How did I put the half in the calculator? At the end, the very last thing I did was I divided by 2. Or you can multiply by 0.5. Divide by 2 is kind of easier. Make sense?
Crazy. Yeah.
And then I'm going to let you figure out Kamala's acceleration for yourself. Should be around 1.5, I think. Put in her velocity, square it, divide it by the height, divide that by 2. That's the hard one on the chart. Force should be easy because you know F equals, what does that mean? Mass times acceleration. Do we have those numbers already in our calculator? Or already in the table? Take mass times acceleration.
Squared.
It is meters per second squared, yeah. For acceleration, right? You guys remember what unit we use to measure force? We use newtons. I think we're too close to the end of class.
What's force measured?
It's 20 minutes though.
Oh, I thought we were getting out of 2. That's 12:15 to get out for lunch.
What's force measured in again? Oh, yeah.
4.
Describe the relationship.
I want you to do number 4.
Is it just? Yeah.
You doing this for yourself? You gotta be able to do this on your own. If you're just waiting for me to fill in the answers and you're copying them down, that won't help on the test, will it? You gotta know how I got those answers. And then I'm putting up the answers so I can continue double checking the work. And you guys check me. Did you get 182 for force? 182.3 newtons?
I got 181.4.
That's because we rounded off differently over here, huh?
Oh, wait, yeah, you're right.
181, 182, I wouldn't mark it wrong. Either way.
As long as it's
If it's in the right range, you're okay. Let's see. Kamala, 61 is her mass, times 152 is her acceleration. That equals 92.72. I'm going to call it 92.7. Okay? When you're done with that, jump down to number 4. Describe the relationship between mass and acceleration. Whenever it asks for a relationship, it's asking you basically, what happens when one thing increases? What happens to the other thing? So if it asks you for a relationship, you start off with something like, when mass increases, the acceleration, whatever it might be, huh? So it wants to know how one thing is related to another. How are they connected? If one increases, what does the other do? Okay. Did you finish number 4?
all the way down to 15, bro. Why? Why are you trying to get that Omicron? Oh, yeah. Guy's trying to get that transformer. I didn't know.
You did everything.
No, I did like it.
All the way over there. Down the road and over to the left. To the left. The other way. That one.
Wait, no, it doesn't. Wait, no. The acceleration slows
Golf
down.
balls, you have one. Hey guys, what did you get for the relationship between mass and acceleration? When the mass increases, the... Okay, now that might be true for these snowboarders, but it is not true when we're talking about a falling object. So here's an example. I'm going to drop a tennis ball and a ping pong ball simultaneously. Which one should hit the ground first? If it's true that more mass means it hits first, right? If mass doesn't matter, they should hit at the same time. Would you say that was pretty much the same time? Right? Check it again. To me, it sounds like the same time. It's a surprise to a lot of people. Now, Galileo did this from the top of the Leaning Tower of Pisa. So in the city of Pisa in Italy, there's a tower leaning over like this far. It's been leaning for hundreds of years. We think eventually it might fall over. But Galileo went up there with two cannonballs, a large one and a small one. Dropped them at the same time from like 200 feet up. Which one hit the ground first? They hit simultaneously. Modern cannonballs would, but in those days, no. It was just like a giant bullet. Just a big chunk of metal flying at you very fast. Would that do some damage without needing to explode? Absolutely. So, not only that, we predict that if you drop a hammer and a feather at the same time, they hit the ground at the same time. Except the feather is held up by air resistance, huh? But wait a minute, there's no air on the moon. Could we do that experiment on the moon? And the Apollo astronauts did this experiment on the moon. They took a feather and a hammer and they dropped it with no air, and the feather fell just like a rock. And they hit the ground simultaneously. If we take the air resistance out of the equation, the feather falls just as fast as a hammer. Well, it's not at the same speed as on Earth because the gravity is different, but it's acting on both of them equally. This is also why a parachute slows down a person, because you increase the air resistance. I mean, think about it. If you jumped out of a plane without a parachute versus with a parachute, wouldn't it be more mass to have that parachute? And shouldn't that make you actually fall faster? But once you open it up, it creates air resistance and slows you down, huh? Right? Okay, so for number 4, I just want to point out, you got to be really careful about this. It is true for this problem that more mass meant more acceleration. But is it true for a falling object? Or even an object rolling down a ramp? They should roll down that ramp at the same speed unless there's something wrong with one of them, like maybe one of them has more friction than the other. You okay with that? Yeah. Let's move on. Now we get to make a graph of the data. Which data are we going to graph? Mass and force. Now tell me this, the first thing you have to do is figure out which is the cause and which is the effect. Does the mass change the force, or does the force change the mass? Tell your neighbor, does mass change force, or does force change mass? If there's more force in something, does that cause it to become heavier? That doesn't make sense. If something is heavier, does that give it more force? That makes sense, doesn't it? Mass changes force. And since that's the case, the cause always goes at the bottom of the graph. The thing that changes the other goes on the x-axis. So this is going to be mass down here. Do you think I'll be looking for titles on the axis of your graph when you do that on the test? Yeah, they're basically 1 point each. So what's going to go on the y-axis? Force, right? Next thing. Not all graphs start with the same number. Sometimes they start at 1,000. Sometimes they start at 50. Most often they start at 0. But whatever number it is they start with, you have to show that on the axis, on the corner. And sometimes one axis might start with 0 and the other might start with 500. So to be clear and to communicate effectively, we have to label both axes. Even if they're both the same number, even if they're both 0, you have to put the zeros on there separately. You can't just put a 0 in the corner. Well, you can, and I'll take 1 point off. If you leave both zeros off, I'll take 2 points off, huh? All right? Because they don't always start at 0, so you need to make that clear. So we're going to do mass first, correct? Now we got to label the numbers. What's my biggest mass back on the data table? How far does my graph have to get to? It has to get to at least 86. What I like to do is round that off to a nice even number. 86, I'm going to round it off to, I'm going to round it even higher. 100, isn't that a great even number? So I'm going to label my graph up to 100. Let's see. Do you think if I count by tens, it would fit? Yeah. You always have to count by the same amount across or up and down, although they could be different from one another. But I can't go 10, 20, 30, 50, 80, 500, 1,000. Can't do that, right? Got to be evenly labeled. Stay true. Keep Tahoe true. So in this case, I'm going to count by tens. Once we get to 100, we've gone past our biggest number and we can stop. You don't necessarily have to use all of the graph. The more of it you use, the easier it is to see patterns and trends. So maybe I would have been better off by counting by fives, huh? And really filled up this graph. That might have been even better. Let's see. 10, 20, 30, 40, 50, 60, 70, 80. Yeah, it'll fit, huh? Let's do this. I'm going to just move some numbers here. I'm going to skip a line. You don't have to label every single line either, do you? As long as they're even. So I'm going to label every second line is going to be another 20. Excuse me, another 10. That's even going to be a better graph, isn't it? If it fits. If it doesn't fit, then I have to go back to what I started with. But it looks like it's going to fit perfectly, doesn't it? So every second line is another 10, isn't it? Now for the vertical, for the force, what was the biggest force that we had? What's my biggest force?
182.
182. And so I want to round that up to a nice even number like what? Like 200. So what if on this one, what if I count by 20s? I don't know if there's enough to count by 10s. So I'm going to go by 20s. 182. So I have to get up to at least 182. I'd like to get up to 200 because it's a nice even number. And it looks like this is going to be perfectly spaced also, huh? So a different scale on the x-axis than the y-axis, but each one is consistent within itself, huh? The x-axis counted every 2 boxes is 10. The y-axis counted every box is 20. That's okay if they're different, but you can't change it halfway through. Let's see, what's next? I'm ready to graph, I think, huh? Once I get the numbers labeled, let's see, Joe's mass was 86, his force 182. So I need to graph a point that's at 86 by 182, something like here, I think. And let's see, what was Kamala? She was 61 and 92. '61 and 92 for her. There's 60. Where's 90? Right about there. So we only have to graph 2 points on this one, huh? But the last thing I want to do is draw a best fit line. And ideally, my line is going to extend the data so I could make a prediction about the amount of force from different masses, something like that. So I did my best fit line but I extended it to fill the entire graph so I could use it to predict how much force would be produced by someone with 50 pounds or 50 kilograms. From up here, I had to get his mass and his force. So this one was 86 mass, 182 force.
We labeled them.
You can, it's not something I would really grade you on. I won't take any points off if they're not labeled. But there is one more thing that we do need to do that I would take points off if you choose not to do it. Exactly. We need a title for the whole graph, huh? So I'm going to give you a couple starting phrases, and then you can choose which one you think makes sense. Remember, a good graph title is going to be a complete sentence that includes both axes, right? So here's one you could start with. Don't have to start with that one, you could. Here's another option. Here's another one. So choose or write your own title. There's multiple choices that would still express the same idea, right? I'll give you one more option. Yeah, anywhere up here is where you would put your title. And so I've just written 4 different titles that you can choose from. You only need one of them, right? Any one of those would be a complete sentence that includes both the X and the Y axis. And then you'd be in good shape. Then you guys do this on your own. Number 6, describe the relationship shown by your graph. What does it mean when I ask for a relationship? We just did one of those a minute ago. What does it mean when I ask for a relationship? How they influence each other. Yeah, that's a good way to say it. How they're connected. The easy way to think about it is when one thing increases, the other thing, whatever it does, it might also increase. It might decrease. It might not be influenced. Yes.
Yeah.
Relationship between 4. Perfect. I just continued a straight line. I didn't choose 40. I just connected the 2 dots in a straight line and extended it straight to wherever it hit that axis. Okay. 20 minutes. I know you did. I need to go too. I'm waiting. Because I've got a job to do here that's more important than my bladder right now. As you do. We got to get you ready for the final exam. So please answer question 6. Describe the relationship. Then we move on to part 2 of the test. The energy section. That was all a review of the FMA, huh? F equals MA. So, relationship. As the mass increases, the force also increases. Pretty straightforward. Hey, do you guys remember how to draw energy diagrams? You have to make your own key. That's part of the grade, is including a key. Doesn't it say that on the assignment right there on the question? Include a key to show the types of energy involved. Right? Remember how to do this? There were squares or rectangles showing the different kinds of energy at the top, halfway down, and at the bottom. What kind of energy do you have to include? You have to include what? Got to include kinetic energy. What else? Potential energy. We're not going to worry about what happens at the bottom if they bounce or whatever. We're going to skip that. We did that on the unit test, but we don't have to worry about any bouncing this time.
Like the very last page?
Of that previous test, we're not gonna do a bounce. Only the fall. Okay? So you don't have to worry. When they hit, some of it gets turned to what? Sound and heat and elastic, right? We're not going to worry about that here.
We don't have to.
I didn't say that.
Just part of it?
No, we're going to do everything that's on here.
Oh.
But
We just don't have
what I'm saying is on the unit test, we did a thing falling and then we also did it bouncing back up.
Okay.
We're not going to do the bounce part. Does this seem familiar to you? Of course, you're going to do this with a pencil. Instead of a computer for the test.
Oh, we have to do it like that. Okay. No, I didn't think that.
Remember doing that? Now for my key, which one do I label as kinetic and which one do I label as potential? Blue is, it was all potential at the beginning, huh? It had the potential to release energy before she started moving. By the time she got down to the bottom, it was all kinetic, huh? Oops, I didn't do that quite right. This is supposed to go, let's see, blue was potential and red was kinetic, huh? And that's all you have to do for that question. The equation to find potential energy. So that's all you have to do on that one is show that it's all kinetic at the top. Excuse me, all potential at the top, all kinetic at the bottom, half and half in between. That takes us to the chart. Remember how to do this math? Here's the equations. I'm going to give you the equations, but you have to know how to use them. What's M?
We're gonna get the equations on that as well.
Yeah,
Okay.
I'll give you the equations. You just have to know how to use them. What's M? M is mass. What's G? Gravity. What's H? And what are we using for height? The 26-meter height, right? Okay. So you'll need a calculator. Please practice on your own to do this for yourself. You need to do it by yourself on the exam, and I can help you right now with the practice one. But I will expect you to know how to do it by yourself on the test. So this is your chance to get help if you need it. You're going to have to refer back to the chart on page 1 to get the mass, aren't you? Who am I looking at? Kamala or Joe? So I have to get Kamala's mass. We have to go back here to get that, don't we? Right? Get the mass from the previous page. So when you have MGH, it's going to be a big number. What was her mass? 61 times 9.8 for gravity times, what's the H? 26, huh? Yeah, just keep going. Don't stop. Yeah, good job, you guys. What unit is this? Joules. And did you get more than 15,000 for your answer? Yeah. Oh, then we have an easy one. How much kinetic energy does she have at the top? 0. How easy is that? You don't have to do any math at all. We just know that she's not moving, so there's no kinetic energy. What about mechanical energy? 15,000 plus 0 equals? And then what about the velocity at the top? What about the velocity at the top? Is she moving yet? She's not moving. So what's velocity? 0. Let's see, what else can we do? Mechanical energy. Well, wait a minute. The law of conservation says that mechanical energy stays the same. So can I just copy that all the way across right away? Mechanical energy is always going to be the same. Once you've calculated it, you don't have to calculate it again. What about halfway down? Potential energy. What do I do? Since it's halfway, I divide that mechanical energy by 2, correct? How do I find kinetic energy when halfway down? That's the same thing as potential energy, right? Then we get to the hard part, velocity. Yeah, let's look at velocity. This is going to be a tough one, so participate with me here. So we should have this number in your calculator already, 7771.4 joules, right? That's kinetic energy. Please multiply that by 2. Hit the equal sign. Divide that by her mass. That was 61.
Oh, wait.
Hit the equals sign. Then you have to find your square root function. At the very end, the last thing you do, square root.
I got lost. So it's 777.4 divided by 2, right?
It's right here. 2 times KE
Okay.
divided by M. Her mass from the first page, I just remember it. It's not right here. I remembered it. Or you go back to find it. Her mass was 61. So divide by 61, and then you finish by square rooting, and I got a velocity of 15.96 and some meters per second. I'm going to keep it as 9.6. That is
I
rounded.
don't think the calculator allows square rooting.
I don't know, but I'm going to give you one of these calculators during the test. Do you want to use one of these to try? And that takes us to the bottom. How much potential energy when she gets to the bottom? She's used up all her energy, right? Or she is in the process of using it. So there's no potential energy. It's all been converted to kinetic. So isn't that the same as the ME? 15,000 and some? And then once again, we have to do the tricky one. Find her velocity. So take your kinetic energy, whatever that was, 15,000 in this case, double it, multiply by 2, divide by the mass, which for her was 61, if I'm remembering correctly. Don't forget to hit the equal sign. After you hit the equal sign, then take the square root.
I lost again.
And it was the same process we just did 22.57 meters per second. So, do you know how to read this?
Boom.
You have to read this. What's 2 KE? There's KE, huh?
Mm-hmm.
What do you do to it?
Find it.
What does that say? That says 2 KE.
Divide it by 2.
No, not if it says 2 KE. That would be KE over 2. This is 2 times. You multiply it by 2. 2 KE, right? Did you do that already?
No.
Then you divide. That line means divide, doesn't it? Divide by M. You either have to look back to see what her mass was, or you have to remember. 61. After you've done all that, you use the square root button. Answer number 9. You don't need me for that.
That's just like naming them. Right?
Yeah, what does PE stand for?
What does the square root button even look like? Oh. I see it.
Yeah, it looks just like that, huh?
I just got 0.
Okay, clear everything. Is it all clear?
Mhm.
Did you hit the clear like 3 times? Okay, put the kinetic energy in there. Okay, now we multiply that by 2. Hit the equal sign. Okay. Now, as I recall, she had a mass of 61. So we have to divide by 61, huh? Over M. So divide by 61.
Mhm.
Did you do that?
Mhm.
With the equal sign.
Mm-hmm.
Now hit that square root button. You should get 22.57 and some. So is this ringing a bell from what we did in the past? I hope so. We do have Tuesday to practice some more. I encourage you to try this again by yourself. So save your work, but also could you download a blank version of this and try it again by yourself and check your answers? I think you could. I think you should. I don't know if you would, but it would be good. Okay? Did you answer number 9? Okay. How about number 10? I bet you can get number 10 done before the bell rings too. 3 parts of the law of conservation of energy.
On Monday, are we gonna go over like the rest of this? Like,
Yeah, we're gonna pick up where we left off on Monday. We'll start on part 3 on momentum.
I didn't even do number
on
9.
Tuesday.
Okay, so please do it.
You didn't even do number 9 either.
I told everybody to do it. Let's see, when the bell rings, I need to speak to Jacob. Both Allens. Michael. Oh, and she's not here. Okay. Never mind, Michael. Jacob and both Allens, I need to speak to you guys when the bell rings. Yeah. Yes.